Thank you. And thank you everyone for being here. Good afternoon. Here I'm bringing a topic about AI-powered image-to-image translation tool to enhance non-contrast CT scans. And my name is Yonggi from Johns Hopkins Computer Science. To give the background, contrast-enhanced computative tomography is an efficient way of detecting and diagnosing cancer for radiologists. Here, the enhancement of the CT scan should be done by the contrast agent injection, and it includes usually 4 phases, that is non-contrast, arterial, venous, and delay, respectively. Doing this is great for detecting tumor, especially for some hypervascular tumors in arterial phase and some, for example, PDAC in venous phase, but it adds clinical risk and increases the cost and scan time. Therefore, to address this problem, we aim to use generative image-to-image AI to enhance contrast in non-contrast scans. Here is an example of the task that we want to enhance the original non-contrast scans to the desired, which is here the venous contrast scans. And here, we found that the commercialized and specialized AI fails to do so. For commercialized AI, it is very popular in our lives. You may use it to create memes, but for precision, it is under concern. For the top bottom, we show the enhancement results to the desired venous phase via the most state-of-the-art AI models. And in the bottom, we show some specialized AI models for specialized in medical imaging just for fair comparison. Therefore, to address this, we put forward a method called SMILE, which is an anatomical aware AI to enhance non-contrast CT scans. The full name is Supermodality Image Learning and Enhancement. This plot can illustrate the pipeline of our system. It is actually based on a very popular Stable Diffusion Generative AI framework, and we introduced 3 specific parts, that is structural, phase, and intensity guidance to complete the enhancement task. Here, the structural guidance is finished by the introducing of the segmentation mask, where it includes the organ structures as well as the tumors, and ensure that in the training process, all the organs are well preserved in enhancement as well as the tumors. The second one is a classifier to ensure that we are enhancing the right way. And the second one is intensity, which is based on the knowledge that organ and horsefield units will rise in different contrast phase. And we use this as a supervision under the training. The core part of our system is that it can enhance the tumors or make it very visible or detectable during the enhancement. Here it is an example of a non-contrast CT where all organs are in low attribute value. And after the enhancement, only the tumor remains in low attribute value to enable us to do the detection of the tumors. This is the result shown of our project. And the first is that we get the best enhancement of global matrix. We get 20% related SSIM, PSNR, and 50 barrier FID. Here you don't need to mess about those computer vision matrix. We just want to deliver that for the image quality, we did all of the best. For the second one, we also add the visualization compression. And this plot shows that our method compared with 9 baselines, where it's hybrid, commercialized, and specialized. The first row is the image quality, and the second one is the zoom-in area for the pancreatic tumor PDAC detection results by a tumor detector. On the left side, you can see for the non-contrast, the detector fails to detect the PDAC, but after the enhancement of SMILE, it is successfully detected, which is marked in the circle area. Following that, we also did correlation analysis to show that we are doing the right enhancements, which means that we are enhanced for every organ in a correct way. Here we introduced the Pearson correlation of attribute values and across all the tests, not only for non-contrast to contrast, but from all directions to another. We did the best of all. And here is the organ volumes correlation, just to prove that all the organs they are well preserved, and we did a good way. For the downstream task, it is the shining point of the project that we did improve the non-contrast tumor detection results by enhancing the non-contrast to the contrast phases. Here, we compare the pancreatic PDAC dataset and with 2 of the state-of-the-art tumor detector. After introducing the SMILE to enhance those CTs, We found that we get at most 20% in sensitivity, overall 10% in AUC, F1 score, and with some modest loss, which is the step for specificity. Above all, this proves that it is working well in virus settings and can detect tumors in this way. On our project, we not only present the SMILE project, but also we get the public release dataset, which is Domain Atlas. It is a dataset collected from whole worldwide and has precise tumor annotations such as for pancreatic, liver, and kidney. Above that, we have AA organ mask, accurate organ at-risk annotations collected from over 100 hospitals all over the world, and we have a hybrid component. One of the important points of this dataset, it is one of the best that is going to be publicly available of such many 88 annotations. Therefore, to summarize my work, we proved that image-to-image AI can enhance non-contrast city in a very precision way rather than just making some memes in an entertainment way. We get over 15 higher SSIM, 20% better FPSNR, 50% better FID to prove that in quality we are out of the best. And the second is the point that early tumors can be made visible or detectable by the detectors. We get 10% higher FI scores. That's a great leap for the detectors. And the last, we provide a paired and voxel register multi-phase data set, which contains around 500 patients, a lot of CT scans, and also tons of anatomical structures from all over the world. Here, you are very welcome to scan the code for the detail of our GitHub projects, or you can connect later for more detailed discussion. And you are very welcome to put any questions you want. Thank you.
Are there any questions from the audience? Okay. A question.
Thank you for that. It was a wonderful presentation. My only question was, and it's probably a little bit up there, but you know, with obviously these wonderful favorable statistics with SMILE comparison to other, commercially available models. I've been thinking about, maybe it was up there. I don't know. Like I don't know if them or not. RSNA. It's another one. Maybe it was. Well, my point was DeepSeek. Like I'm thinking, was there comparatives to anything around the DeepSeek world, the Chinese world, or anything around that as far as model comparison? Because obviously that kind of like created a lot of disruption when that first launched.
Okay, I got you. So you mean for the DeepSeek model specifically? Or
yeah. So I saw this word. I don't know if that coined 3. I didn't Google it because I was looking at your thing, but or any of the I didn't recognize if anything was from the DeepSeek world, and if there was, if you had any comments around just again your results were given what's coming out of that paradigm as far as AI.
Okay, got you. Thank you for this question. At first, DeepSeek is not trained with medical-specific data, but also they are provided with medical-specific data. So to ensure the fair comparison, you cannot introduce like something that doesn't know that at all to compare with this medical-specific and for enhancement domain. So here, the DeepSeek family is not involved.
Okay. Thanks.
Thank you.
So, okay, go ahead.
This is very interesting work. I'm wondering if this model can be adapted to kind of identify areas of high vascularity within the organ, within the tumor, because that might be of interest when it comes to response prediction and that kind of stuff.
Okay, thank you for this question. And my answer is yes. Actually, this is a plug-in and play part. You just need to, here I want to show you the component. You just need to maybe change some of the structural segmenter or some disease identifier here, and our system can enhance the patterns to here to identify the lesions or something you mentioned.
So have you guys looked into the lower level features that are contributing more to the model deciding to enhancing a certain area to generate a contrast intensity? Like what are those features on a high level? Have you guys looked into some feature importance and all that kind of stuff.
Okay, if I'm not if I'm not going wrong, so the features you mean is by some biomarker, is that correct?
Yeah, like, so all the features that are more important when it comes to contributing to the
Prioritization,
final.
80-20 rule type thing.
Okay, gotcha. And first, we present the feature which is the most common is visual, and it's also we can provide some, for example, for a thyroid density, and as well as for the fat density to serve as biomarkers for more types of tumors.
All right, thank you so much.
Thank you.
Okay, thank you so much.